Good afternoon. I'm Norman Wildberger, and we are in Lecture 5 on number theory and algebra in Asia in this course in the history of mathematics. So we've been talking mostly about Greek mathematics up till now, and now the story shifts eastward. In the beginning, the first few centuries of the realm after Christ, the Greek mathematics began to decline, and although there were still some notable Greek mathematicians in the later years, notably Ptolemy, around 200 AD, and Diophantus, around 200, 300. And Ptolemy was especially important in that he wrote a very influential book called the Almagest, which translates into something like the Great Treatise. So this was a work on astronomy. He was an astronomer, and it was very influential with the Arabs who came later. Diophantus was sometimes called the father of algebra, although that's probably not an entirely fair name. He wrote books on what are called Diophantine equations, or equations with rational solutions. And he did introduce some kind of algebraic formalism, ways of shortening mathematical reasoning so that it's not all just long words, but also some symbols. So this is kind of a transitional figure to the modern age where we use a lot more symbols and a lot fewer words. Now, when I've quoted Euclid and Archimedes, you'll have remembered that I used a lot of English words. The Greeks, the ancients, wrote things out longhand. Gradually, as the centuries went by, more and more symbols were used. And we're going to see some of that today. So today we're going to leave the ancient Greeks. The ancient Greeks kind of period perhaps ends with the dramatic death of Hypatia, who was one of the only female mathematicians in our story, especially in the ancient world. She lived in Alexandria. She was the daughter of Theon of Alexandria, and she wrote books on commentaries on earlier authors, and also had a thriving school. Her end was rather sad. She was killed by a Christian mob because there was lots of religious turmoil in Alexandria around the year 400 to 500 AD. And that story is told in a very recent movie called Agora. So if you haven't seen that, it's very worthwhile having a look at it. It's gives a good account of the time of Alexandria in the late Alexandrian period, and the story of her life and death. Okay, so after the Greek period died out, the Mediterranean became Roman, and the Romans contributed very little to mathematics. They don't enter our story at all, really. And it was really only through a completely indirect means that mathematics was reestablished in Europe more than 1,000 years later. So there was a kind of 1,000-year gap where the Europeans were almost entirely out of the picture. And the story goes eastward, and today we're going to talk about the Chinese contributions, the Indian contributions, and the Arab contributions. Okay? All important civilizations, cultures that had thriving mathematics as part of what they were doing. Okay, so let's talk first about the Chinese. The Chinese their contributions to mathematics were more in the algebraic and number theoretic direction. They were interested in equations and systems of linear equations. the kind of things that we study in first year linear algebra. So in one of the earlier works is 300 AD, the mathematical manual of Sun Tzu, whom we don't know much about, but he wrote this work. And so the systems of linear equations were involved in this. Very important thing called the Chinese remainder theorem, which I'll describe in a few minutes. The Chinese also were interested in computations. They knew how to compute square roots. They certainly knew about Pythagoras' theorem, and no doubt discovered it independently, or probably discovered it independently. It's hard for us to know because there would have been interaction between these ancient cultures. There was trade. People did travel around. Okay? So ideas were exchanged, but we don't really have a very good idea of who influenced whom. Later on in the Chinese work, around maybe the 12th or 13th century, there's a very clear reference to Pascal's triangle. So maybe this is around the 1300s. Pascal's triangle, of course, is that which appears in the binomial theorem when you expand out a plus b to the fourth. For example, you get a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And those coefficients are part of this famous triangle where every element is the sum of the two elements directly above it. Pascal's triangle. But it's Pascal was in the 1600s, so this is quite a few centuries earlier before that. The Chinese also knew about the Euclidean algorithm, which is a very important device which we've talked about, and that was in the Han Dynasty, somewhere between 200 BC and 200 AD. So I want to talk a little bit about their work with systems of linear equations. This should read. And I suppose we should add here that they were interested in solutions with in integers, as well as others. So here's an example of the kind of problem that the Chinese were interested in. So suppose that you are on the number line and you can only take integer numbers of steps. And suppose that for some reason you can take a step of size 79. Or you can take a step of size 23. And those are the only possible steps that you can take. Okay? So maybe we have two kind of robotic arms or things that move. This one can always move 79 in either direction, and this other one can move 23 in either direction. And if we start at 0, the question is, can we get to 1? So, can we go from 0 to 1 using steps of size 79 and 23 only. Well, this amounts to a certain equation. So what we're really asking here is, suppose we go m steps of size 79, and we also go n steps of size 23, where m and n are possibly negative or positive. Can we get a combined displacement of 1? So we're really looking at this linear equation with the idea of finding integer solutions. Okay. So we want integer solutions to this linear equation. And this is the kind of question that the Chinese found interesting, and the Hindus also found this kind of equation very interesting. So how do we do it? Well, the answer is yes, you can do it, but it's not entirely obvious, and it comes down to the Euclidean algorithm. So how do we use the Euclidean algorithm? Well, let me go up here. And so suppose that we divide 79 by 23. 79 being the bigger one, so we'll divide it by 23. It goes 3 times. That's a total of 69 plus a remainder of 10. And you may remember that in the Euclidean algorithm, so we started off with these two numbers. Now we do the same thing with the numbers 23 and 10. We divide 23 by 10. Well, it goes 2 times 10 plus a remainder of 3. And then we divide 10 by 3. 10 is equal to 3 times 3 plus 1. And finally, well, 3 is just 3 times 1. And there's no remainder. So if we were looking for the greatest common divisor of 79 and 23, we would at this point know that the greatest common divisor is 1. It's the last non-zero remainder that we got. Okay. So the greatest common divisor of 79 and 23 is equal to 1. That's what the Euclidean algorithm shows us. Now what we're going to do is we're going to take those steps and we're going to reverse engineer them. We're going to go backwards to express 1 as a combination of 23 and 79. That's our aim. What we're going to do is we're going to start with the bottom equation, or actually the second bottom equation. And so maybe I'll do it here. We're going to start with equation 1 and write 1 as 10 minus 3 times 3. So I'm using the 3 and the 10. Now that's all right, but we're not interested in 10 and 3. We're interested in 23 and 79. So we go back up a step. And in this step up above it, we can see that 3 is a combination of 23 and 10. So we're going to replace this 3 with the corresponding combination of 23 and 10. What does that give us? Well, the 10 stays where it is. Minus 3 times what? Well, from here we see that 3 is equal to 23 minus 2 times 10. And I'll just leave it in that form. And then I'll group all the 10s together and all the 23s together. The 10s, there's 3 10s. 3 10s minus 3 23s. 7. Yes. 7 10s. Thank you. Minus 3 23s. Okay, now maybe I'll go over here. Okay, well, now we're going to do the same thing, but we're going to replace the 23 here. No, not the 23. We're going to replace the 10 with this 10 up here, expressed in terms of 79 and 23. So 1 equals 7 times. The 10 is going to be replaced with 79 minus 3 times 23. And we still have the minus 3 times 23 left over. And when we put that together, we see that we have 7 times 79. And how many 23s do we have? Minus 21 from there, minus another 3, so minus 24 23s. And so we've written 1 as a linear combination, as a combination of a multiple of 79 and a multiple of 23. So if you wanted, back to our robotics problem, so the answer is you need to take 7 steps of size 79 and then 24 steps of size 23, and then you'd be exactly 1 from where you started. And so you can see the power of the Euclidean algorithm, and the ancient Chinese who knew the Euclidean algorithm were well aware of this method. So a problem that Sun Zi gives us that illustrates the Chinese remainder theorem is this. So he says, find an integer n satisfying 3 conditions: that it should be congruent to 2 mod 3, that it should be congruent to 3 mod 5, and congruent to 2 mod 7. So what does this mod notation mean? So n congruent to 2 mod 3, what that means is that n is equal to a multiple of 3 plus 2. Or another way of saying it is that the remainder on division by 3 is 2. Okay, so how could we solve this? The numbers are not too big, so we can probably solve it just with trial and error. So let's see if we can do that. So we've already said that this first equation really amounts to this condition, n equals 3k plus 2. And the second equation amounts to the condition that n is equal to 5, some other number, say L, plus 3. So we need to, at least, just to satisfy these two equations, we need to make sure these things are equal to each other. So 3k plus 2 equals 5L plus 3. Can we solve that? Well, we can simplify it a little bit. We can say that, well, that's like 3k minus 5L equals 1. And now that's very much like the kind of equation that we've just been talking about. We know how to solve that kind of equation. So we can, for example, find solution k equals 2 and L equals 1. From which we get that n might be what's the common thing? It's got to be k is equal to 2, then it's 8, and L equals 1, so it's 8. All right. Now that's not the only possibility. In fact, now you can add multiples of the multiple, the common multiple of 5 and 3, namely 15. So a more general solution now is that you can set n equal to 8 plus any multiple. I'll use some other letter. I haven't used m yet. Say 8 plus 15m. And if it's of this form, then it will satisfy these first two conditions. And now we only need to make sure it satisfies this one as well. And that one is the condition that it's congruent to 2 mod 7, so it's a multiple of 7. Let's say 7t plus 2. Well, that's another equation of the same kind. 15m minus 7t equals minus 6. Okay, we could do that. M equals 1 I have, and this is 3. So if m equals 1 and t equals 3, then we have 15 minus 21, that's minus 6. And so from this we can sub back into here, and so finally we get that n equals 23. And that's one, there's actually others, but that's one solution to that system of linear congruences. That's actually found in Sun Tzu's manual. Okay, what is the general theorem, of which this is just a special case? So here's actually the Chinese remainder theorem. It's that if the numbers p1, p2, up to say pk are relatively prime, so no common factors, for example, they could be prime numbers, that would work, then this system, n is congruent to R1 mod P1, where R1 is some number less than P1, n congruent to R2 mod P2, same kind of thing, down to n congruent to RK mod PK, always has a solution. N. So we can solve not just this particular case, this is a very special case. We have 3 linear equations, congruence equations. In fact, we can have as many as we like. And as long as these numbers here are relatively prime, they don't have any common factors, then we can do something like this to find a solution n. We're guaranteed that there's always a solution n. It's a very pretty theorem. It's quite powerful. It has lots of applications. So later on, Euler and Gauss use this theorem in their studies. So it's a rather good and interesting result. I have a little bit of a personal connection with this theorem because the very first theorem that I published was in number theory. And I was interested in Diophantine equations when I was younger. And I was interested in equations like x cubed plus 3y to the 4th equals z to the 5th. You've all heard of Fermat's theorem, where you have x cubed plus y cubed equals z cubed. So I was interested in what happens if you change the exponents a little bit, maybe throw in some coefficients. And my theorem was that as long as these exponents are all relatively prime, for example, then there will always be an infinite number of integer solutions. Even it doesn't really matter what the coefficients are. And so this, later on, I went back to this and I thought about this some more, and I developed what I call the power method for Diophantine equations. Which is well described on my website. So if you go to my website, you can actually find an applet that actually allows you to solve Diophantine equations. You plug in a Diophantine equation, and maybe, not necessarily, maybe it will spell out a solution for you. So it's on my website. There's something called the Diophantine equation solver. It's a program that was written for me by a former student here at UNSW, Michael Leeming. It's a lovely program, in fact. And you can try it out if you have an interest in number theory. You can try out this equation. It's surprisingly effective for such a hard problem. Okay, so now let's turn to the second important civilization on our list today, the Indian civilization. And we're talking not really about the ancient Indians, but the sort of more modern Indians that were flourishing around from around 500 to 1200 AD. And there are some important names here also. Let me give them to you. There was Aryabhata, around 500. There was Bhaskara. There were actually two Bhaskaras. There was one around 700, and then there was another one, Bhaskara, the second is usually called, around 1100. And in here also Brahmagupta, also around 700. What were the Hindu mathematicians interested in? They were not so interested in geometry. They did do some geometry, as I'll show you. They were mostly interested in algebra, in astronomy, and in trigonometry, and also equations, solving equations with integers. And they made important contributions to these subjects. They also were responsible for a crucially important development, which I'll talk about later. So aside from these things, there's something else that they did, which was so important that in my view it's probably the single most important scientific achievement of all time. If you had to rate all scientific developments, they were responsible for the most important one in my view. I'll tell you what that is later, but let's now talk about these things here. So first of all, let's talk a little bit about geometry. Brahmagupta discovered some beautiful formulas relating to quadrilaterals that live on a circle, so-called cyclic quadrilaterals. Okay? Not all quadrilaterals live on a circle. The ones that do are special. They're called cyclic quadrilaterals. And if the sides are, let's call the sides A, B, C, and D, then he discovered this following area formula. The area is the square root of S minus A, S minus B, S minus C, S minus D, where S is the half perimeter, 1/2 of A plus B plus C plus D. So problem 10. Show how Heron's theorem, or Heron's formula, follows from Brahmagupta's. He also proved another remarkable formula having to do with that diagram. He proved that if we label these vertices, say capital A, capital B, capital C, capital D, that the length AC, so the diagonal there, it was given by the expression AC plus BD, AD plus BC divided by AB plus CD, which seems to me a very lovely formula. Not at all easy to find. Yes?
Where is that coming from?
No, that's separate. But problem 11 is write down the formula for the other diagonal for BD. So they did do some work in geometry, but it was certainly nowhere near that of the ancient Greeks. And this here is probably one of the highlights of it. One thing that they did make an important innovation to was trigonometry. So Ptolemy, the foremost astronomer of the Greek period, had compiled a table, a trigonometric table, to allow one to make calculations effectively. And he used what he called the chord. So if that's an angle in a circle, let's say the circle is radius 1, then this side here might be called the chord of theta. So Ptolemy tabulated values for the chord depending on the angle, so that if you knew the angle, you could look up what the corresponding chord length was. Now, the ancient Greeks did this. The Hindu mathematicians changed the emphasis, and they changed it to considering what we now call the sine of the angle. So still a circle of radius 1, let's say. Then we would say this thing here is the sine of theta. And they recognized that this was probably a more useful, or to them it was more useful relation. And they tabulated values of sine theta. Okay? So that trigonometric function and others was due to them. And maybe over here I can squeeze in, let's have a drawing of the graph of the sine function. So here's the sine function, perhaps in an unfamiliar way for you. So what it looks like. And what are the values here? The values here are 3,000, 4,000, roughly. Now you're probably used to the sine taking on values between -1 and 1. But to the Indian mathematicians, they preferred it to take on a value. The maximum here was I guess 3438. Where does 3438 come from? Well, they were measuring in angles, in degrees. So there were 360 degrees around the circumference of the circle. And they used the ancient Babylonian system of mod 60. So the ancient Babylonians had a base 60, and trigonometry has been going on for a long time. They adopted the Babylonian system. So in the Babylonian system, you measure angles in degrees, and then you also have minutes and seconds. And there are 60 minutes in a degree and 60 seconds in a minute. So for very fine measurements, you divide a degree into 60 little pieces. Okay, so for this reason, they wanted to think of the circle as being essentially having 360 times 60 units around it. So okay, whatever that number is, what is it? It's 0036, 221,600. In order, if that's going to be your circumference, then your radius ought to be, well, this is going to be 2 pi r. They knew what pi was roughly, so they could calculate what r was roughly, and the closest value is 3,438. So that was a very convenient framework for studying trigonometry, because then you don't have to work in these crazy radians like you people are forced to. A more natural 360 degrees, a much nicer system, and the tables work out to be more integers and less decimals. Fractions were still problematic back then. Okay, so here's the picture of the sine function in these little bit unusual units. But one of the Indian mathematicians, Bhaskara, this is the later Bhaskara too, I believe, he discovered a remarkable approximation to the sine function, which I don't think you even learn in today. So there's this other function. Okay, it looks something like that. Maybe it does other things. It's not a parabola. Okay, it's actually a rational function. And what is that? So this is Bhaskara's approximation to the sine theta function. His approximation was sine theta is, okay, it's this radius r, whatever that is, times 4 theta, 180 minus theta, divided by 40,500 minus theta times 180 minus theta. Okay, so as a function of theta, it's what we call a rational function. It's a polynomial divided by another polynomial. But it means it's relatively easy to calculate. And this is a remarkably good approximation. So in these units, in the units where this height is 3,400, this approximation differs at, the worst difference is 6. So 6 out of 3,000 is not too bad at all, approximation. That's the worst discrepancy between the real function and its approximation. So this, of course, this could be now used to, instead if you didn't have a table of signs around, they didn't have calculators, of course, you could use this as an approximation. The story of the Hindu contribution to trigonometry has many other things in it, and a very good source for this and lots of other information about trigonometry is Glenn van Brummelen's book, which is called The Mathematics of the Heavens and the Earth. It's a history of trigonometry applied to astronomy mostly. Okay, so the Indians also made important contribution to Pell's equation, which we've seen already. Pell's equation has its origin in Archimedes' cattle problem, which I read to you. I remind you that equation was x squared minus ny squared equals 1. And we remember that there's an obvious solution. X equals 1 and y equals 0 is an obvious solution. The question is, are there any others, and how do you find them? We're looking for integer solutions. Well, trial and error is a good way, and you can certainly discover for different values of n, where n is a square-free number, you can hunt for them. And here's a table of some of them. So here is capital N, and here are the smallest values, the smallest non-zero, non-trivial values for x and y of Pell's equation. If n is 2, we've already seen the solution 3, 2. N is 3, there's the solution 2, 1. 5, get 9 and 4. 6, 5 and 2. 7, 8 and 3. A little bit further on, 10 is 19 and 6. And 13 is 649 and 180. And of course it keeps going. And eventually we get to 61. And 61 is kind of an interesting value, because the smallest solution to Pell's equation are these numbers. 176631949. That's the x value. And the y value is 226153980. That's probably a little bit more challenging to find by trial and error. Question?
Are these solutions for x and y unique for each n?
No, there's a whole, for every n, there's an infinite family of solutions, as I'll soon point out. These are just the smallest ones. The smallest ones. Okay, so it's probably safe to say you're never going to find this with trial and error. You need some understanding of this equation. And Brahmagupta had such an understanding. So Brahmagupta knew how to solve Pell's equation. And in fact, this solution, it goes back to him. It has to do with the continued fraction of n. And this equation became important much later on. So later on, Fermat, great French number theorist in the 1600s, rediscovered, well, I guess other people had discovered Pell's equation, but he, as a challenge to his contemporaries, asked them, I think, to compute a couple of values, and he knew that 61 was tough. He would certainly not have known about Brahmagupta's work. But he also knew that 61 was a particularly tricky value to find. So he knew about 61. There's a general fact here about Pell's equation, a key fact, which is that you can always solve it. Okay, so this is actually only established by Lagrange in the 1700s, that Pell's equation always has an infinite number of solutions. So I want to tell you about an important identity that Brahmagupta discovered that's sort of a key to understanding some aspect of this. So here's an identity that goes back to Brahmagupta. What is it? It's x1 squared minus ny1 squared times x2 squared minus ny2 squared equals x1 x2 plus n times y1 y2 all squared minus n times x1 y2 plus x2 y1 squared. All right, so problem 12, verify this is correct. So it's true for any n. And there's one special case that you already know about, the case n equals minus 1. In case n equals minus 1, this becomes x1 squared plus y1 squared times x2 squared plus y2 squared equals x1 x2 minus y1 y2 all squared plus x1 y2 plus x2 y1 squared. Does that look familiar? That's perhaps the most important fact about complex numbers. What is that fact? That if you're working in the complex plane and you have one complex number x plus iy, or x1 plus iy1, and another complex number z2, which is x2 plus iy2, then it's usually stated in this way, that the modulus of z1 times the modulus of z2 equals the modulus of z1, z2. But this form here is actually about the squares, which is more natural form. Okay. It's really a quadrants equation between quadrants of 3 complex numbers. So this is a very key, very profound and important framework for complex numbers, and it's a very special case of Brahma-Gupta's identity. And why did he think it was interesting and important, this identity? Because it allows us to generate solutions to Pell's equation from existing solutions. So, for example, if you know, let's say, that x1 squared minus ny1 squared is equal to 1. Suppose that's a solution to Pell's equation. And you know that there's another solution to Pell's equation. Then you can combine them to get another solution to Pell's equation, because 1 times 1 is 1. You see that? You take this solution, you take this solution, then you use x1, x2, y1, y2 to come up with this number and with this number. And then these two numbers also have the property that this squared minus n, this squared, equals 1. So it allows you to generate more solutions from if you already have 2 solutions. Okay, but still the question remains, how do you exactly compute this how do you find one non-zero solution? How do you come up with a solution like this? What's the algorithm? That's too hard for us to talk about, but I will mention a paper of mine which just appeared last year. It's called Pell's equation without irrational numbers and it's in the Journal of Integer Sequences. But I think it gives the simplest possible derivation, the simplest known algorithm to come up with these numbers starting from n. It's an algorithm that it's much simpler, I think, than most treatments, and it only uses essentially first-year linear algebra, a bit of multiplying matrices. So you can have a look, you can find it online very easily if you're interested in Pell's equation. All right, we'll take a break, and then we'll come back and describe what this most profound contribution of the Hindu mathematicians was.